Hey, welcome back. And so we are beginning a new unit today, and this one is pertaining to the solar system. So we have branched out in the universe, started here on Earth, branched out to the sun, and then the family of stars, and the Milky Way galaxy, and the rest of the galaxies, and took a look at the universe as a whole with modern cosmology. Now we're going to rein it back in and find our way back to our own solar system, and take a look at each of the planets of our solar system and the origin of our solar system, and even exoplanets, extrasolar planets, perhaps around other stars, we'll also look at a little bit. So new unit, new study guide, so make sure you're finding all your resources online. The PowerPoints are online. Your study guide, of course the videos will be on there as well for you as a good reference. And so our what are we summary for today is that we are comfortable. We live on a planet that has evolved right along with living organisms to where we are very comfortable. This is our home world, Mother Earth. And so yes, we are comfortable. Our planet is just in that Goldilocks zone from our star, the sun, that makes it just perfect for life on our planet. So we are very comfortable here. Okay, so the way this unit is set up, chapter 6 will talk about the innermost 4 planets that we do call the terrestrial planets, the Earth-like planets, Terra, standing for Earth. And then chapter 7 will talk about the outer worlds, what we call the Jovian planets, or the Jupiter-like planets. So it's just going to take us through looking at the planets, doing a nice comparison of those, and then chapter 8 will help us to take a look at the origin of the solar system. After we've gone through all the planets, we're going to look at the similarities and the differences, and then chapter 8 pretty much helps summarize why we're seeing the differences that we do see and the similarities that we do see about our planets. And so our terrestrial planets will be our first stop here in the comparison of our planets. Okay. Yeah, and so taking a look at, and they do include the moon in this one, but comparative planetology is what we will be using for this, but it's a comparison of one planet with another. You're looking at their similarities, you're looking at their differences, so comparative planetology, and that's the best way to analyze the worlds in this amazing solar system that we do have. And you do have an appendix in the back of your book that has a celestial profile card for each of your planets, which will have all the particular details about the planet. And I'm not going to be so tied up about particular detail, you know, like what's its size, what's its temperature, these kinds of things. Those are important facts, but the approach that we're going to be using is what are the basic differentiation that they go through, how did they form their craters and basins, and what has happened over time with the kind of slow surface evolution. So we're looking more at a theme, an overall view, rather than facts, teeny tiny facts about them, which you can always look up in your celestial profile if you're interested in doing that. So this is sort of more of a comparison thing that we'll be taking a look at. So we're going to visit 5 Earth-like worlds now. 5, well, only 4 inner planets, but we end up including the moon in that. So we'll be looking at Earth, Earth's moon, Mercury, Venus, and Mars as our inner, or what we call terrestrial Earth-like planets. So yeah, the moon being on our itinerary, it's a natural satellite orbiting Earth, so it's not one of the planets, but it's very important in looking at it. It's a fascinating world kind of its own. It's a planet-like object, and it's 2/3 the size of Mercury. So it's, Mercury's pretty small, and the moon's, 2/3 of the size of Mercury. But it does make a nice comparison that we can use for our list of our other worlds that we're going to be also looking at. So you have a page in your book. I'm trying to figure out that page number. A couple page numbers in there where it's actually comparing the 5 worlds that we're about to study, and it sort of has them here with comparative sizes out there. But Mercury is slightly more than 1/3 the diameter of the Earth, has no atmosphere, and it's heavily cratered. Okay, you might not be able to see that too well, but heavily cratered. Here, of course, the blue planet is strikingly blue, right? So the planet Earth is going to be our basis for the comparison. So just as we use the sun as our reference in studying the stars and the Milky Way galaxy in our study of galaxies, we're going to use the Earth as our reference for our terrestrial planet. And it's a water world, so we're the blue planet, widely covered by liquid water. It makes it very unique. It has polar caps of solid water, so ice, and our atmosphere is rich in water vapor. So we are the water planet for sure, and little water droplets in our clouds and our beautiful thin atmosphere. You can see the swirling of the clouds there, and so really water plays an important role in all 3 physical states. Solid, liquid, and gaseous form of water really makes the Earth unique. The Earth's moon's only about 1/4 the size of the diameter of Earth, and it is airless, so no atmosphere, and also heavily cratered. So there might be a connection there, whether you have an atmosphere and how much cratering still there. Okay, and so then over here we have Venus. So it's almost the size of Earth, 95% of the diameter of Earth. It has a very, very thick cloud atmosphere, okay, that really hides its surface from view. It does have a solid surface though. And it is seen through Earth-based telescopes. It just looks like a featureless white ball. Definitely, it's got a lot more going on there. We're seeing volcanoes on Venus, so geologically very active in there. So Venus has impact craters, volcanoes in it, and solidified lava flows. So it's had a very active past and is continuing to be very geologically active, we would say. Mars, slightly more than half of Earth's diameter, has a thin atmosphere. So it does have a remnants, a little bit of an atmosphere, but a very thin one. Rocky, cratered crust. It is marked also by volcanoes, so it's had some activity, geologically active, some old lava flows, and then polar cap of solid carbon dioxide in Mars's poles. So carbon dioxide, though, not water there. But just kind of have a basic kind of general comparison there on those first few pages. But yeah, diameter is like the first thing we look at. The moon's very small. Mercury's not even that much bigger. Earth and Venus are about the same size. Mars is kind of medium in between that. And we will find that size is a very critical factor in determining kind of a personality of our planets. The smaller worlds tend to be geologically dead, as I mentioned. Venus being geologically active, certainly Earth is geologically active, Mars as well. But those small ones, they've actually cooled off really rapidly and are what we call geologically dead now. And the larger worlds can be geologically still active in there. So looking at a core, mantle, and crust for our planets, and even, the moon as well. So the terrestrial world, so our inner four planets that we're talking about, are made up of rocky material and metal. So rocky material, like what we have here on planet Earth, we use that as our reference, and which is more of a lighter, crustal type of material, very low density. So think of our oceanic crust and our continental crust, a lower density rocky material. The mantles are a more dense rocky material. And then the cores of our terrestrial planets are metal, okay, and iron, even maybe iron and nickel type of cores, okay, and so they are differentiated. During their formation, they completely went molten. The entire planet did. And so as it cooled off after its formation, it did differentiate into layers. So this differentiation phase that it went through. And of course, that's going to differentiate according to density. So the low density ones are going to float to the outer portion. The most dense material is going to be driven towards the center of our little worlds. And so that's why we've got this differentiation of, a metal core, a dense rocky mantle, and then a very low density outer kind of crust when we look at it. So mantles composed of dense rock between the cores and the crust kind of thing. So sort of what we have in common with most of our, let me write up a comparison that the main things we see in common with all of them. So these are the terrestrial planets. Okay, they're basically, small in comparison to our outer planets. They're small, dense, okay, rocky worlds. Rock and iron. So rock and iron. They all have little to no atmosphere. Okay. Of course, the Earth has an atmosphere, a very thin atmosphere. Mars has an even thinner atmosphere. Venus has a pretty decent atmosphere, a rather thick one. Mercury has no atmosphere whatsoever. The moon has no atmosphere whatsoever, either. And so, small, dense, rocky worlds, little to no atmosphere, especially compared to the outer Jovian. Those have extremely thick atmospheres. Now, also, they have few to no satellites. Okay, and satellites is a term we use for moons, okay? So, of course, the Earth has one moon, the moon, and the other ones, Venus has none, Mercury has none, Mars has two that we'll take a look at, but few to no satellites, and definitely in comparison to our Jovian worlds that have many, many moons or satellites to those, so few to none. And then we include this in here, no ring systems. Okay, what we mean by that, if you think of the outer planets, Saturn right away is the one with the striking rings, the beautiful rings of Saturn, obvious even in a little rudimentary telescope. You can see the rings of Saturn. Now, in comparison to those Jovian worlds, the interterrestrial planets have no ring system. All of the Jovian worlds, not just Saturn, have ring systems. They're not as obvious as Saturn's, but they all do have them. So terrestrial planets do not have the ring systems to them. And I mentioned here, we are mentioning the differentiation process. All of our terrestrial planets went through a differentiation process. But again, the rate that they did some of this might differ between them, but they all went through this process of differentiation. And then this next thing here about when your planets were, young, the solar system was young, and their surfaces were subjected to this heavy bombardment period. There was still a lot of debris out there, space debris that hadn't quite accumulated into a planet yet. So there was still lots of debris out there, and there was a lot of battering that happened, a heavy bombardment period, we call that, from these little leftover, what they call planetesimals, large fragments, but yet they weren't cohesive into a planet yet. So they call them planetesimals, and the fragments. And so they all kind of went through this cratering formation. All of them got battered, okay? And then they underwent some basin formation, cratering and basin formation. So they're kind of talking about there. And again, the rate that this happened, kind of differed for each of the rocky worlds in there. And then the last thing we're going to kind of think about is the surface evolution, the slow surface evolution, how it changed over time. Certainly Earth's surface has changed over time with weathering and erosion that all occurs, that we see occur nowadays. But how that occurred, or the lack of it occurring on our other planets in comparison to the Earth, has a lot to do with, what kind of atmosphere did they have, or lack of atmosphere. So did it even occur at all, and why it didn't occur is something that we do want to make a bit of a distinction on. So this is kind of how we want to do our comparison in there. Set that up kind of like that. So cratered surfaces are very old, okay, in that early bombardment period. So if you have a geologically active planet, like the planet Earth, for example, lava, the heat from that internal part of the planet is trying to well its way out to the surface of the planet. From that internally hot planet and core in there, that heat's trying to make its way out to where it's cooler. That's kind of a temperature gradient that we see. Heat wants to flow from places where it's very hot to places to where it's cooler. That's the gradient of temperature, heat flow. And so lava could have made its way up through some of those cratered surfaces and smoothed them out, welled up and kind of smoothed out the landscape. So some of our planets might not have visible craters anymore, or very few craters visible, because of that welling up of the lava from below, okay? And so most of our debris in the solar system eventually got coagulated into the planets, and so there's not a whole lot out there. Yeah, there's still some leftover debris, but it wasn't like in the beginning during their formation. So, the surface is younger than the cratered areas. So we can set up kind of a timeline. If you see old kind of cratered surfaces, we know that that happened during the heavy bombardment period. And if those craters are still there, well then there wasn't a lot of geologic activity to smooth those out, okay? Thinking of the moon, it's a heavily cratered surface. Thinking of Mercury, a heavily cratered surface. And so these are in appearances to pretty much what they look like way, way back in their formation. Soon after their formation, when they finally solidified and got battered, okay? There hadn't been a lot of surface smoothing out on those worlds, okay? So yeah, you can guess that the surface is younger than the cratered areas if they're all kind of smoothed out from the lava. So we want to follow the energy, as I was mentioning, that heat trying to escape its way out from the interior of the planet, which is kind of left over from the formation of the planet when it had completely went molten, right? That's really hot to melt your planet. And so that's still trying to make its way out. But something else that we get is heat that gets generated by radioactive decay. And so our rocky material in there will contain elements that are what we call isotopes that are, and some of those isotopes are radioactive, they're unstable, and they will break down and release energy, and the heat energy coming from that. And so that radioactive decay heat is trying to make its way out as well. So it must flow outward towards the cooler surface. So it's trying to get radiated out into space with that temperature gradient that we have. So we can kind of follow that. And as that heat's trying to make its way out, it will cause, we've heard this term before, convection currents in the mantle. So we first talked about the convection currents in the sun, how that hot rising gas created the granulation or that mottled surface on the sun. Well, in here, the convection is in making currents in the mantle, okay? And so, well, I don't have that up there, but the mantle region, and it's trying to make its way, and so it will create hot rising material, cools a little bit, sinks back down. So a convection cell that occurs. Also, the kind of liquid outer core in there in differential rotation creates a magnetic field, all that churning that's going on, creating a magnetic field. It will drive what we call plate motion. So some of our planets, not very many of them, but the Earth in particular, does have what we call plate motion. It's a plate tectonics theory that we have in geology. But the Earth's crust is on plates that move. And so as you get all that convecting material from the mantle welling up, the plates move around. Sometimes they move apart, sometimes they come together, sometimes they shear past one another, and so that's going to create all sorts of topography or the shape of the land in that, and can result in earthquakes. We call them earthquakes, but seismic activity, the motion of those plates, faulting, so you can get breaking and rupturing of the Earth's crust, or the crust in general, volcanism, so the welling up of that hot mantle material as it makes its way to Earth's surface. We see that expressed as volcanoes or volcanism, we call that. Also mountain building. And so this is how some of our, when you get two continental plates coming together, they kind of buckle up and create our mountain ranges. And so all that motion happening because the heat's trying to flow upward towards the cooler surface in there. So it makes a large world like the Earth what we call geologically active. Okay, so I mentioned how some of these other ones are geologically dead. That would mean that they have cooled off now, that their mantles and their cores have cooled off now and solidified to the point that they don't have that convection happening. So their plates, they're not going to move, okay? So the moon and Mercury have cooled very fast. Recall that they are smaller in comparison when we looked at that comparison page. So they had very little heat kind of moving outward, and so now they are relatively inactive, or what we would say geologically dead. Okay, so they're very inactive. They don't have that molten material any longer. So Mercury and the moon, we see craters, heavily cratered, and we do see some plains in there, so some higher regions, mountain regions as well, even some flatter surfaces in there like plains. When you look at those small worlds, Venus, surface of Venus is completely hidden by a very thick, kind of cloudy atmosphere, yet it's there. It does have a very thick atmosphere, more so than Earth's atmosphere. Mars, being medium-sized terrestrial planet, it actually has a very thin atmosphere. It has a little bit of one, but very, very thin. And we're going to see how those differences in atmospheres have a lot to do with the evolution of the planet, and they really did have quite a great variation in their evolution because of either a lack of an atmosphere, too thick of an atmosphere, too thin of an atmosphere, or the Goldilocks planet Earth, the just right atmosphere. Very comfortable, keeping us very comfortable. Again, like our what are we summary. We are comfortable. Okay, so why do some worlds have atmospheres while others do not? Again, the size matters and the temperature of the planet. So, just how close or how far away are they from the sun? Their placement of their proximity to the sun would have a great effect on that as well. But size does too. So why some have it, why some don't on there. Where did these atmospheres come from? Okay, the ones that do have their atmosphere. So we're going to have to study the geologic history of these worlds. So we'll kind of be looking at, atmospheres in there as well as we go through these. And see, it did play a big role in the evolution of these and how they differed. So Earth, again, is going to be the basis of our comparison for the other terrestrial planets. So we're going to start with the Earth. My favorite planet is the Earth. And it's a very active planet. I think already we're getting the feel of how dynamic our planet is when we did look at, the motions of Earth. The rotation, the daily rotation, and the revolution around the sun, the yearly revolution. So a lot of motion going on, always in motion. And so it does have a great effect on the planet as a whole, that motion. So the molten interior and the heat trying to flow out, as I mentioned before, is going to be driving our volcanism, our earthquakes that we talked about in there, a very active crust plate motion. The plates on the crust, the crustal plates, always in motion, believe it or not. They are always moving, sometimes pulling apart, sometimes coming together, because the Earth's diameter is not getting bigger or smaller, okay? So that means there are some places where the crust is moving apart and there's an active upwelling of new magma material creating new crust in some places. And then in other places, you're getting crust coming together. One of the plates are going to descend under the other one and get destroyed and melted, recycling of crust. So that keeps our planet's diameter in balance. It's not getting any bigger and it's not getting any smaller. So there's a nice balance going on with plate motion. So we have a very dynamic, very active Earth. Okay. So our surface, as we talked about, the blue planet is very strikingly blue. So almost 75% of its surface is covered by liquid water. So the liquid water seems to be very important, especially in surface evolution. Okay. Our atmosphere also has significant amounts of oxygen in it, which makes it very nice for us that need to breathe the oxygen in there. So what we know about the formation of Earth, we would expect it to have been differentiated into the layers. So, iron core, dense rocky mantle, and then the lighter, less dense crust in there. So kind of what evidence reveals about Earth's interior? How do we know? How do we know what's going on? We can't dig that deep to find out. So we use the study of earthquakes, these seismic waves. So kind of theory versus observations. And so trying to get out the mass, the density of our Earth as a whole, like the average of it. Earth's mass divided by its volume is going to give us sort of an average density of 5.5 grams per centimeters cubed. So that's on average, though. We did talk about very dense core, little denser rocky material, and then the less dense. So, but on average, about 5.5. So the density of the Earth's rocky crust is only about half of that. So, less dense crust. Um, but when we can get an earthquake, now we have what we call seismographs all over the world, basically, these instruments that we place in the ground. So anytime we get any kind of shaking or earthquake, it can record the little seismic waves that travel through the earth and also along and out the surface of the earth as well. A variety of seismic waves that we can study, record and study. So each time an earthquake occurs, these seismic waves will travel through the interior and register on a seismograph. And we've got these very strategically placed all around the world, and you can actually pinpoint and locate the position of the epicenter of your earthquake. All you need is 3 seismographic stations, and you can get that worked out. But yeah, so what we're looking at here, as an earthquake is sending seismic waves through Earth's interior. We call those body waves, seismic body waves. And they're in a variety here that they're talking about a P wave and an S wave that they're going to distinguish. P stands for primary and S stands for secondary. Sorry, they're both seismic waves. Primary and secondary waves, primary travel faster than the secondary waves. That's kind of how they got their names in there. But our P waves will travel through solids, liquids, and gases. So they'll travel through all sorts of medium. But our S waves will only travel through solids, okay? So they don't go through liquids and gases. So that difference between those seismic waves helps us set up what kind of medium do we have in the internal structure of our planet. So these seismic waves have been very valuable. And they talk about an S-wave shadow, meaning that S waves can't penetrate through a certain region in the interior of our planet. P waves make it all the way through, okay? But for some reason in here, as we get close to the outer core, there's an inner and an outer core in our planet, the S waves are deflected. This makes the seismologists believe that that outer core is liquid. Otherwise, the S waves should have been able to go through it if it was, solid. So that makes us think we have a liquid outer core and an inner solid core, because it's so dense there that they believe that the metal, is solid in there. So this can help us, just studying the seismic waves, get a feel for what's going on with the layering or the differentiation of our internal Earth. We don't have to dig down and find it. We can use these seismograph data from the seismic waves. Okay, so these waves had showed that the Earth's interior is divided into a metallic core, okay, a dense rocky mantle, okay, right on out here, and a very thin, low-density crust. That low-density crust is actually oceanic crust and continental crust, which there are variations between those. The continental crust would be the least dense of all. Oceanic a little bit more dense, but basically a thin, low-density crust. And we can see kind of this liquid outer core because of our study of the seismic waves. That does help us in there. Okay, so the core's density is about 14 grams because they're thinking composition is probably mostly iron, so they can get that density greater than lead. And then composed of iron and nickel, deducing its temperature. So the core is hot. And remember that 6,000 Kelvin, well, that's almost the temperature of the sun, a little hotter than the surface of the sun anyway. Of course, it's much hotter in the interior of the sun, but the surface of the sun, if you remember that, the photosphere, was about 5,800 Kelvin. Well, so the internal part of our core is estimated at 6,000 Kelvin. So high pressure, though, in the middle here keeps the metal a solid at the very center, but then that it has a liquid outer core. And that kind of sets up a magnetic field kind of thing happening because differential rotation between the solid inner core and the liquid outer core, kind of creates this dynamo that creates a magnetic field in there. Very interesting how they learn about that. So the P waves and the S waves, as I mentioned before, traveling kind of like sound waves. They can penetrate through liquids, solids, and gases. Our P waves can. And they're more of a push-pull type of a body wave that goes through. If you think of a slinky, I didn't bring my slinky today, but if you've ever played with a slinky and you kind of go push-pull and have that on a table, push-pull, you see the propagation of the wave energy in the slinky. That's what our P waves are like, a compressional type of a wave. The S waves are more a side to side. Say you took a rope and you shook it side to side, so an S wave, a shaking type of a wave in there. And so traveling through the earth in there. So we can deduce the size of that liquid core by how much of a shadow, of an S wave shadow that get through and where they don't. Okay, so here S waves are getting through, here S waves are not getting through. So we can figure out just how large that inner liquid core is by using this method in there. Fascinating stuff. So the magnetism gives us further clues about what's going on in the core, as I just kind of mentioned before there. So we do have convection kind of stirring that molten material in the liquid outer core, and so that's a very good conductor of electricity, and so it will give us a magnetic field through that dynamo effect that I mentioned, creating our magnetic field that we have. But the mantle is a deep layer of dense rock between the molten core and the solid crust out there, so it's sort of a transitional region. The mantle is it's solid, but yet it is capable of flow, which is very important when we talk about plate tectonics, the motion of the plate's crust. Remember, pulling apart in some places, coming together in other places. It acts, it's molten, but yet it can flow, and it liken it to, say, some warmed candle wax, not to the point that you have melted your candle wax, but you've warmed it and you can kind of bend it and it kind of flows, if you think about it like that. So the mantle material can flow very slowly, and then the brittle crust is on that mantle material, and so it's flowing as the mantle flows, and the crust is brittle, so it can break into plates, we call that. So yes, there is that motion, the rocky outer crust of the low density rocks in there. And so I talked about that discrepancy between the continental and the oceanic crust. So there's some differences with density going on in there. Of course, continental crust thickest where we have the mountains in there, where with our continents, thinnest with the ocean as well. So 35 miles thick under the continents and 6 miles thick with the ocean. So a little thinner with our oceanic crust than our continental crust. And so it floats on the mantle basically, and sets up sort of this plate tectonics, plate motion of that. So the motion of the crust combined with the action of, we have running water on our planet. We have the liquid water, oceans, rivers, lakes, this kind of thing, ponds. We've got water on our planet. So it really does make the Earth's crust highly active and changeable. Okay, so evolution of the crust, we can erode, slow surface evolution through erosion and weathering that occurs can really change our surface over time. Okay, and so there's a little page in there, important things to note about the active Earth. A wonderful little diagram here that really does explain many of the plate motions, and then the expression of the plate motions on our surface of the Earth in the form of volcanism, mountain building, the mid-ocean rises that they talk about in here. So the geologically active Earth, and most definitely the earthquakes, the volcanism, the mountain building, are linked to the motions of the crust, like I mentioned, to plate boundaries, and what we're talking about in there. And so, volcanoes, okay, the molten rock emerges from volcanoes, coming from the mantle and not from the molten core. Okay, that mantle material can melt and then work its way up. The difference between a magma and a lava: magma's beneath the Earth's surface, lava's when it goes up to the surface. And so the lava doesn't have all that dissolved gas that the magma has. But yeah, so it's coming from the mantle, not the core, okay, in there. But it's working its way up, right? And you're going to get some plate motion happening. Off over here, if we took a look at that saying South America, you could also think of North America, for that matter, out on the United States western coast, okay? But we're looking out on the western coast of South America here, but you can also think about our western coast. This is a region where, so we've got the Pacific Ocean there, the continent here, right? And that happens to be a plate boundary where we are getting convergence. We're getting two plates coming together. So you've got the continent here, and you've got your oceanic crust here. They're converging, okay? The more dense oceanic crust is going to be the one that subducts beneath the continental crust. When it does that, all that friction is going to melt, okay, the oceanic crust. So that's what we're seeing down in here. As that layer subducts beneath the continental crust, we're getting the melting happening, okay? And you can see it kind of welling up. And so we see that expressed on the surface of the continent as a volcano. So a volcanic arc, continental volcanic arc, we call that. And so yeah, lots of volcanism on the west coast of South America. That's where our volcanoes are located, on the west coast of North America, the west coast of the United States. Mount Rainier, right? Mount St. Helens out there. So we do have volcanoes, and that's why we see them where we see them, due to plate tectonics, a convergence of the plate boundaries. So volcanism, we get our earthquakes out there on the west coast of the United States, right? California region, because of plate motions, the slippage of the crust, and creates seismic activity, the shaking happening. Good explanation for the earthquakes out there. It's out of plate boundary, okay? Out here, so now we have the Atlantic Ocean, and in the middle here, we're seeing that this is a divergent plate boundary, okay? So we're getting the spreading of two plates, okay, being pulled apart. Well, when that happens, you're going to get an upwelding of magma that's rising up, creating new crust in here. So you've got a mountainous ridge, so a mid-ocean rise, we call that, right down the Atlantic Ocean. So we call that the mid-Atlantic ridge, and it is built up from the upwelling of magma because those plates have diverged. Okay, so mid-ocean ridges or rises are from plate boundaries as well. Okay, so a few things there. Of course, mountain building's another one. I'm not sure if we've got, more pictures of these things. So the continents of the Earth's surface have changed over time. Well, we need lots of time for this, but over periods of hundreds of millions of years. And as we're learning, the Earth has, a very long history, a 4.6 billion year history. So it's been afforded the time for this evolution to occur. So they talk about 200 million years ago, where because of all the plate motion, at one point all of the continental material was together in what we called Pangea, a supercontinent. It had all assembled for all lands together. Pangea kind of translates into that. So that's that term, Pangea, is what it was called. And then it began to slowly pull apart again, okay? On for the ride, right, of the plate boundaries, the continents were kind of along for the ride, and they began pulling apart, okay? Pulling apart. This is 65 million years ago. Here's today. So that now, over time, we do see the continents in their location where they are today, but at one time, they were all together. So a definite evolution that has happened, and it is because of plate tectonics, the motion of the plates. So mountain ranges, the Grand Canyon, are recent products of Earth's active surface. But yes, here's that just winding its way through the Atlantic Ocean, the mid-ocean rise, okay? Over here, rimming or ringing the Pacific Ocean, we call that the Ring of Fire. Interesting name, like the Johnny Cash song, the Ring of Fire. But all around the Pacific Ocean, so circum-Pacific, are subduction zones. Remember how one crust is subducting under the other? That's going to cause the melting and the volcanism. So the Ring of Fire is where that's coming from. That is a circum-Pacific, so around kind of the Pacific Ocean, volcanism like crazy all around through there. We can also get rift valleys. So now let's say we have a continent, so continental and continental crust that pulls apart. That's known as a rift valley, and a very famous one is right in through here in the continent of Africa, where the ocean has actually gotten up in there, and that's where the Red Sea is now. That's a rift valley, okay, where two continental crust has been pulled apart. Things like our Appalachian mountains. So the convergence of continental crust. So say we have two continental crusts coming together, they buckle up and they create the mountain ranges. So again, the explanation of seismic activity, so earthquakes, volcanism, our mid-ocean rises, all, the Ring of Fire, so all that volcanism, rift valleys, these can all be explained by plate tectonics, the motion of Earth's crust. Dynamic planet. I could go on and on about the Earth and plate tectonics. So if you like this stuff, you might join us in the geology course, because we go more in depth with this. So yeah, and this is just sort of showing the formation of the Grand Canyon is a little bit more recent type of and we're talking geologically speaking, recent activity. But it has undergone, millions and millions and billions of years of evolution. So, yeah, and they do, for the age of these things, they do age the rocks. So they're in Australia, onwards of 4.3 billion years that they have age dated some of those rocks. So it's in good kind of agreement with the age of our planet. Okay, so that's a little bit about the plate tectonics and the landforms, the topography that we see from that. So looking at the Earth's atmosphere, the beautiful swirly white clouds, that thin atmosphere, although it's thin, it really does protect us and keep the Earth very comfortable for us. Keeps us within a temperature range that is very conducive for life on the planet. So how did it form? How has it evolved? So has it changed? And are we changing it with our, climate change kind of thing, or human-induced global climate change? So are we changing it? And I would have to say yes, we are for that. But kind of thinking about the Earth's atmosphere, it can help us understand what might be going on with our other planets, those ones that don't have an atmosphere. Or maybe they have a very thin one, or maybe they have a very thick one. We're like in the Goldilocks zone there. So Earth's first atmosphere was its primary atmosphere, okay? Containing gases from the solar nebula. So as the sun was kind of forming that solar nebula material, in there. So things like hydrogen, surprise, surprise, hydrogen, is like most in the universe, right? And maybe a little bit of methane in it as well. But gases such as carbon dioxide, nitrogen, water vapor at that time probably would have been cooked out or, maybe outgassed from the rocky material, from the metals. So that may have kind of been sort of a secondary sort of thing. Planets are accreting those little planetesimals. As I mentioned, they're not quite a planet, but they're still pretty large fragments. Those may have had some icy bodies in them, and then planet Earth kind of scooped those up sort of thing. Maybe had some water in it, ammonia, maybe had some carbon dioxide in it. So, that big bombardment period. So maybe Earth kind of incorporated some of that. But that primary atmosphere, they believe, was rich in carbon dioxide, nitrogen, and some water vapor in there as well. So the atmosphere that we have today is what we call a secondary atmosphere, because as things evolved, life evolved on the planet, it actually added more oxygen to our planet. So once we were cooling down enough, from that differentiation stage, cooling enough, we were able to pool together the liquid oceans, okay? And so a lot of that carbon dioxide that was in the primary atmosphere got dissolved in our oceans, and even in the sediments, things like limestone, right? A calcium carbonate from the carbon dioxide was in that. And so our oceans really removed a lot of the carbon dioxide from our atmosphere, that primary atmosphere. So it formed, the limestone, other mineral sediments that we have, some silicon dioxide, so our rocky kind of crust in there. So the oceans transferred the carbon dioxide from the atmosphere to the sea floor, the oceanic crust in there. And so then it was able to be enriched in things like nitrogen, so mostly nitrogen in our atmosphere. And then over time, the oxygen increased. The removal of the carbon dioxide is really critical to Earth's history. Carbon dioxide is one of those gases that we may have heard of, greenhouse gases. It's one of them, okay? And so they're doing a comparison of our atmosphere with a greenhouse. So greenhouses are usually, a clear glass type of a house, all right, that will allow the sunlight, so visible light, to penetrate through the window, okay? And it will go in there, and that's kind of a shorter wavelength, right? A visual kind of wavelength, shorter wavelength. And then get into the greenhouse, and so then you got all your plants in there that are going to absorb that visible light, right? That's part of its photosynthesis. It needs that visible light. It will absorb that and then re-radiate that energy in longer wavelengths, in the infrared wavelengths of our electromagnetic spectrum, a little bit longer wavelengths, okay? Those little bit longer wavelengths cannot get back out of the glass, okay? So that in effect then re-radiates that infrared energy and will warm your greenhouse. We call it the greenhouse effect. Maybe a little drawing might help with that, how we liken that to the greenhouse effect. Okay, so here we have the sun. How well you're going to see that. But it has, coming in, I'm trying to make these a little bit shorter wavelengths, okay, visible wavelengths, visible light. So I'm writing short, and then that little symbol, the lambda symbol for wavelength. So it's coming in, and I've got, I don't know, we'll make a little flower here or something, a little flower, leaves and whatnot. And so that short wave radiation's coming in, getting absorbed by everything in your greenhouse. And then the plants will re-radiate that in longer wavelengths, okay? radiating out in every kind of direction, but longer wavelengths. Infrared. Okay, so that's an, oh, I hope you can see that. Infrared. Okay, wavelengths. These are longer wavelengths, right? The infrared wavelengths. Those get trapped, okay, because the glass is what we call opaque to infrared radiation, okay? So it doesn't allow it to go back out, so it just bounces back around and continues to warm and heat. That's known as the greenhouse effect. So the glass, or our atmosphere, being transparent to the shorter visible light wavelengths, it can get through our atmosphere. But then once that gets in there, gets absorbed and re-radiated as infrared radiation, if you have carbon dioxide in your atmosphere, a greenhouse gas, it will block that longer wave radiation, the warming radiation, from exiting out to space, okay? It will get intercepted by the carbon dioxide and re-radiated back down to the Earth's surface, in essence warming it. So the greenhouse effect is what we talk about. This is also like the parked car effect. So every year they talk about how, you know, try to get this message out there. Don't leave your small children or your pets in a parked car, right? Because it gets really hot, and it doesn't even have to be very warm outside. You know, you could maybe have a 60-degree day or a 70-degree day, and you think, oh, I'm just gonna pop into the store, leave my kid or my dog in the car, and I'll be right back out, right? Well, you know, if you ever go to Walmart, you see everybody in town that you know, and you're gonna chat, and time will get away from you. And you come back, and then there you've got a problem on your hands, because that car, that temperature will go up 15, 20 degrees just in the first 10 minutes. And so you've got a real problem on your hand. So that parked car effect, you know how your car is hot when you get back in it. Greenhouse effect thing going on. Similar to what our atmosphere is doing for us. So the more carbon dioxide you have in your atmosphere, the more of a warming effect. So that's why they kind of talk about the global warming being related to or correlated to the increase of carbon dioxide that we are putting out from the burning of fossil fuels and various other things that are humans doing this. So yeah, a similarity then, short visible light coming in, no problem, goes right through the carbon dioxide, it's transparent to the short wavelength radiation, but yet the longer infrared or terrestrial radiation, we sometimes call that, it blocks it. It's opaque to that and won't allow it to go through. And so in essence, you are warming and raising the temperature, the surface of the planet. And we need some of that warming, right? Because that keeps our temperatures comfortable and within a, you know, a high and a low range that is very conducive for life on our planet. When we take a look at Venus, we're going to see that it kind of has a runaway greenhouse effect. It is on steroids. It has so much carbon dioxide in its atmosphere that it's a runaway greenhouse effect. So hot, 880 degrees Fahrenheit there. Mars, on the other hand, with a very thin atmosphere, it is more like a refrigerator type planet, very cold, and it gets broad swings of temperature change from day to night on Mars, minus 220 degrees Fahrenheit at night and about 60 degrees Fahrenheit during the day. So great temperature swings because it has a very thin atmosphere. So the atmospheres will affect the evolution of your planet for sure. Okay. So yeah, here they're mentioning the global warming, and here they have some data on the carbon dioxide parts per million, and how along about the 1800s, the Industrial Revolution, when humans began the burning of what we call the fossil fuels, so our hydrocarbon fuels, releasing carbon dioxide as a byproduct. So it has gone up, 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 up. this chart only goes to 390. It is now over 410 parts per million, the highest that we've seen it, okay? These PowerPoints are several years old. So we are actually above about 410 parts per million now. It just keeps going up, okay? And so that will then be translated into the temperatures that we see, and it's globally temperatures that are warming. It's also the oceans are warming too. So we do call that global warming, and the correlation is that it is human-induced. Scientists vastly are in agreement on that. So that's a critical issue, as you can imagine. It affects agriculture, changes our climate patterns, so we might get more intense storms, or it might move the location of our intense storms. It might give us droughts, long periods of droughts. It might give us 100-year historic kind of years of flooding. Various things can go on. So major flooding, major droughts kind of thing going on, and things we're seeing today. And as I mentioned, when we do visit Venus, you're going to see a planet dominated by the greenhouse effect, a runaway greenhouse effect on Venus. Okay, so yeah, when the Earth was young, of course, it didn't have a lot of the free oxygen, but when organisms began to make their way, photosynthesis, of course, absorbs some of the carbon dioxide, but then releases oxygen, and so it began to kind of bubble out of the ocean and saturate the ocean with oxygen, and then it began to bubble out into our atmosphere, releasing that free oxygen. So yeah, ocean plants kind of began to manufacture that oxygen a little faster than what could be dissolved in the water. And so 2 to 2.5 billion years ago, the atmospheric oxygen began to increase, so kind of like our secondary atmosphere at that time. So it went hand in hand with living organisms in there. So oxygen is O2, right? A diatomic molecule. But we also have, thankfully, a layer of what we call ozone, so a triatomic molecule of oxygen, so 3 oxygens, an O3 up there. And we have kind of good ozone and bad ozone, but the good ozone is way up there in a layer in the atmosphere we call the stratosphere. So way up there, 30 kilometers up, and this one will help the planet by blocking out the harmful gamma rays, X-rays, and the majority of those UV, ultraviolet radiation, okay? A little bit of UV comes through. That's why we want to make sure we wear our sunscreen and wear our sunglasses so we don't get cataracts kind of thing. But that is very protective to our planet by blocking these lethal rays that come from the sun. Right, and I think we mentioned that back in an earlier chapter about the Earth, the atmospheric windows, right? Yeah, and so that's good ozone. If we get the ozone down towards Earth's surface from a lot of our engines, combustion kind of engines can put ozone out, those old, lawnmower kind of things too. And that can really cause some problems, add to smog. You might hear about ozone days. You might want to take a bus or, carpool on those types of days, or stay indoors on those type of days because it's bad for people with breathing problems. And so we talk about a hole in the ozone. Back in the 70s, this was a big problem because of the refrigerant that we use to kind of cool our electricity generating power plants. Those were the big culprits. They were using the CFCs, the chlorofluorocarbons. Chlorofluorocarbons have chlorine and fluorine in them, but it's the chlorine that was combining, kind of breaking apart our ozone molecule to a single oxygen and an O2 molecule, right? Oxygen, O2 is fine, but that single oxygen would combine with the chlorine, but then it wouldn't allow that to come back together as an O3 molecule, an ozone molecule. So we were getting this thinning of the ozone layer. And that's bad for us, right? So they have since, gotten rid of the CFCs, right? Which is great. We're not putting out any more of that chlorine to wreak havoc, but the damage that we've done, that chlorine's still up there. So we're not adding any more, but there is still a problem with the ozone layer in there. So harmful ultraviolet radiation, skin cancers are on the rise, problems with cataracts on the rise because of that thinning of that ozone layer. Very important. It's an environmental issue, and it was a human-induced. We changed our atmosphere enough that we're seeing some problems because of it. A human-induced problem that's separate from the global warming problem that we've got going on. So public health kind of concern there. It's also of interest astronomically because when we go to Mars, remember how that was a much thinner atmosphere. We're going to see an effect of a planet with no ozone layer whatsoever. Okay, so it's such a thin one that it can't form an ozone layer, and we'll take a look at what happened to Mars in there. So a nice way to do a comparison is looking at the atmospheres. So here we're taking a look at some stages the Earth formed in the inner solar nebula as opposed to the outer solar nebula. These terrestrial planets are the inner part in there. And so it passed through 3 stages, and these stages, happened on all of the planets, but the rate that they happened could differ. But we want to try to pull together a logical kind of history of our planet in here. So let's kind of take a look at the history of our planets in there. That first stage, as I mentioned, was the differentiation, where we were getting, a core, mantle, crust. Again, they did differentiate and occurred kind of early on. And then, radioactive decay could have released from the rocky material, and so that's why, our planet's still very geologically active in there. And so differentiation, that stage. The second stage, as I mentioned, the cratering and the basin formation. And so that didn't happen until everything had cooled down on the surface to where you could get the battering of still that debris out there, the heavy bombardment period, and getting the craters to form. Heavy bombardment of the early solar system cratered the Earth just like it did Mercury, just like it did the moon, right, that are heavily cratered. All of them went through that. And so the largest craters were called the basins, so almost like a bowl-shaped basin. And some of that, big enough that it cracked through the upper mantle to the point that some of that mantle material could well up and maybe even smooth that out. So it may have smoothed it completely over. On planets with liquid water like the Earth, those basins could have filled in with water, and those would have become the first oceans on the planet. But as that debris in the solar system, and that nebula, they call it, cleared away, the rate of those impacts would have slowed down quite a bit and fell to now is lower kind of present rate. Yes, the Earth, does get hit. The meteors do kind of streak through, but on a much lower level than it did in the young solar system. Okay, and then we've been kind of talking about the slow surface evolution. Okay, and so it's been going on, quite some time, the past 3.5 billion years, changing over time, right? Plate tectonics, we were describing that. Sections of the crust sliding over and past one another, the subduction zone, pushing and buckling up mountain ranges like the Appalachian Mountains we have, shifting our continents, plate tectonics, rifting, rift valleys kind of thing, all the volcanism and the earthquakes that we see. So moving air and water, so very important that we have running water on our surface. water is like the major erosional agent. In its liquid form on our planet, in its ice form or solid form, glaciers do a tremendous amount of erosion. And even helping us with our hydrologic cycle, water vapor creating the clouds, which causes the precipitation, that sort of thing. So water is major on this planet for evolution of the surface in there, wearing away geologic features, right? So almost all the traces of the first billions years of Earth have been smoothed over and changed, destroyed because of the active, very dynamic crust that we have and the erosion over time. So an incredible planet, the planet Earth here. So life on the planet began kind of at that secondary atmosphere stage. It replaced, the primary atmosphere. But that might be unique to planet Earth, and that may not have occurred on the other. But all of the terrestrial planets pass through these stages. But again, differences among those. Their masses, their temperatures, their compositions may have been, a little slower, a little later, but creating surprisingly different worlds for sure in there. So the Earth is more or less our nice reference planet to get us going here. The moon, okay, we're including the moon in this. There is no atmosphere on the moon. Temperature differences is very extreme from shade to sunlight in there. Two kinds of terrain that we talk about on the moon. One that we call Maria. These are kind of the smoother lowland portions of the moon. They call them Maria, a Latin word for seas, like oceans or seas. Because when they were first viewing these, think of Galileo when he was first kind of viewing the moon through his little telescope, it kind of looked and resembled an ocean. They didn't know. So they called them Maria for that reason, or a mare, meaning one, singular, and Maria for many of them on there. So it looked like seas to them. But that's sort of the darker gray that you see if you look at the moon, even just with the visible eye. You don't need binoculars or anything to see that difference. The lighter colored are the highlands or the mountainous regions. Remember, Galileo did see mountains on the lunar surface, and so those would be mountainous kind of regions. The moon looks very bright in the night sky, seen from Earth. Its albedo is 0.06. I mean, it reflects only about 6% of the light that hits it, but it looks really bright in contrast to the night sky. But it would probably, in reality, look more like a gray world, like kind of a dark gray. But when you go to the moon, you're going to find those craters. Even in a nice little telescope or binoculars, you can see the craters on there. The highlands are marked heavily by craters as well. And in contrast, the smooth lowlands, okay, the mare or the Maria, contain fewer craters. What's going on there? Why aren't they cratered as well? Kind of thing. So evidence of the craters were formed by impact. Again, heavy bombardment. The moon was there as well, and it was getting bombarded early on too. And so sometimes you can see ejecta. So impact, and then it spewed out kind of that rocky material in rays kind of look to it. But the craters range in size from giant basins to even little microscopic micrometeor pits that they talk about in there. But most of those craters are pretty old, from when long ago the solar system was kind of beginning to form, and we talked about that heavy bombardment period. But from the comparison of the ages of the moon rocks that were collected from the Apollo mission and brought back, the heavily cratered highlands and the somewhat younger less heavily cratered Maria. So it seemed like the highlands were very heavily cratered, hadn't undergone any kind of surface evolution, but the Maria were smoother and less cratered, okay? Less heavily cratered. Sets up kind of a timing that we can think about on here. So 12 Apollo astronauts visited the moon, the Maria and the Highlands, in 6 expeditions between 1969 and 1972. I think last year we were celebrating the Apollo anniversary kind of thing on that. But and they have plans to go back to the moon. I think they're on target for 2024. And this one will have the first woman astronaut that will set foot on the moon. So very exciting. We want to go back to the moon. But the rocks that we found, both in the Highland and the Maria, were very typical of what we see here on our planet as lava, hardened lava. And the Maria are actually ancient basalt lava flows. And so they've got some pictures here. I actually brought some actual earth rocks that are similar in comparison here. I don't have any moon rocks. Those are in the Smithsonian kind of thing. But a resemblance of what a earth rock would look like, and that we know to be lava, basaltic type lava, versus what we're seeing on the moon, okay? One here, we call it a vesicular basalt. It has little vesicles or bubble looking things. So as the magma's coming up, still a very warm kind of a body, the moon, the gases are bubbling out as it gets towards the surface. Almost like a little can of soda that you've got a lid on top of your soda. Well, there's carbon dioxide in there. There's gas that's dissolved in your soda. When you release the lid on your soda, all those bubbles, all the carbon dioxide fizzes out, right? Because it's not under so much pressure. As that molten material is coming up and it reaches the surface, all those gases bubble out, and sometimes they get frozen in time, right? And you see all the vesicles in there. So that's what we do, see that, a vesicular type of basalt. Over here we have what we call breccia. These are moon rocks here. Rock fragments, so that's just evidence of the shattering and the fragment bombardment that the moon underwent. But they get put together by pressure and heat, okay? And so lots of little fragments that are sharp and kind of jagged looking. And off over here, rocks exposed on the lunar surface became pitted by some little tiny micrometeorites in there. That's an anorthosite. Let me switch over to camera here. I don't know how well these are going to show up for us, but I'll have some earth rocks here that are similar to the lunar rocks that they're going to talk to us about in here. This one here is a vesicular basalt. Okay, try to get that name on there as well. But this is from lava, a basaltic type of lava. We call it scoria. This one's a black one. You saw on that other one it was kind of a reddish tinge to it. But that would be like what we're seeing in the Maria location. This one is breccia. Okay, you're seeing all those fragments, okay, those jagged fragments that have been compressed together. So we do see breccia here on our planet as well. And then this other one over here is anorthosite. I've got my name. Very similar to a volcanic ash. That's probably not showing up very well. Volcanic ash. Let me see if I can zoom. Not zoom. Let's try that. See what happens. I don't know if that helped any. Volcanic ash similar to the anorthosite of the highlands that they're talking about in here. So these are earth rock representatives that are very similar to the moon, which can give us some clues about how the moon formed here that we'll talk about some hypotheses. But anorthosite, a light colored rock that contributes to the highlands and that bright color, contrasting the dark Maria. would have been among the first to kind of solidify and float kind of towards the outer portion of the molten material. And then many of the rocks are the breccias, so those are fragments, so that just tells to the history of the bombardment period and fracturing the rock. And then they kind of get cemented together by heat and pressure in there. So yeah, it does show how extensively shattered by meteorites the moon was. So kind of a powdery dust that gets kicked up by the astronauts' boots is the anorthosite, kind of volcanic ash here that we would talk about. And then of course the Maria were the basaltic, the vesicular ones with the little vesicles. So kind of looking at the lunar geology, the lunar rocks, can piece together sort of the history of that moon, okay? And so now they've got some different hypotheses, and they think they've got the one that matches best with evidence, but these are some of the proposed hypotheses on how the Earth got its moon, okay? So many of these here. And the first one, the fission hypothesis, proposes that the moon broke off from a rapidly spinning Earth, and that, you know, it's just a piece of Earth material, okay, is what they're thinking of for the fission hypothesis. The condensation hypothesis is thinking that, well, the Earth and its moon condensed out of the same cloud material from the solar nebula, and so they just sort of blobbed and got kind of near one another and gravitationally become bound to one another. That's the condensation hypothesis. The other one is the capture hypothesis, and there's actually another one. And this one is maybe the moon formed somewhere else, okay, and kind of made its way and got close to the Earth, and the Earth captured it in its gravitational pull. That was one. That does happen with other moons, or with other planets, but maybe not so much. Maybe it doesn't really explain what we're seeing in the evidence, but that's an option there, a capture hypothesis as well. And these had some problems with them. They didn't survive the comparison with actual evidence, what we were seeing in the lunar geology. So, you know, it was pretty similar to the Earth material, but yet, you know, had some variations. So here in the 1970s, they came up with a new hypothesis that combined some of the traditional ones as well, pieces of them anyway. And this one's called the large impact hypothesis. So that in sort of the Earth's history in there, that the moon formed when almost a Mars-sized planetesimal, so a very large planetesimal, smashed into the baby Earth, the proto-Earth, as it was forming, and really made it go molten, completely molten. So they're calculating that the collision would have created an ejecta that ended up kind of getting in the disk around the Earth, sort of a debris disk. So here's the impact, right? And then the ejecta that would have given, and notice how it's completely kind of molten there. The Earth is molten in there, and kicked out that debris, and over time that got locked, all that debris kind of got locked up into Earth's orbit around it, and solidified and created our moon that's, you know, locked, kind of tidally locked to us. And it explains many of the, you know, similarity in the rocks sort of thing, the ages of the moon rocks that they formed. They're just about as old as the Earth, so making good sense that this happened about the time when the Earth was a proto planet. They call that a baby planet. So collision kind of occurred off-center, spun the moon and the Earth system very rapidly, creating a high angular momentum in there. It allowed, you know, the differentiation to happen, material falling together to form the moon would have been hot enough to melt, right? It would have melted it. And the first evidence of the highland, that anorthosite, right, in the moons, those are the oldest rocks in the moon, formed by differentiation of large quantities of molten material, and the lighter density stuff kind of floated towards the top, the anorthosite, the highlands kind of thing. So it does pass a lot of the tests of comparison, and it's great that we actually have the lunar rocks so we can hands-on study those. This one, the large impact hypothesis, is the one that is right now, to the best of our knowledge, the considered likely to be the correct hypothesis, the going hypothesis in there for the formation of the moon. Large impact. Okay, so very small. The moon's very small. It's only about 1/4 the size, the diameter of the Earth. And so that escape velocity is very low. So it's been unable to hold on to its atmosphere. Okay, so, you know, things like hydrogen and oxygen that buzzes around too fast, it can't hold on to that. Gravitationally, it can't even hold on to those. So it can't form an atmosphere around it. And it's small, so it ended up cooling off rather rapidly. And so, you know, that internal heat flowed outward into space. It didn't have an atmosphere to keep, you know, its surface warm or anything. So it really cooled off, very small size, cooled off rapidly. And so the Apollo moon rocks are a great source of the timing of the events in the moon's history. And they show that the moon must have formed in that mostly molten state because it did kind of differentiate low density and then the more dense vesicular basaltic lava. And so now they refer to that newborn moon as a magma kind of ocean. I mean, it was molten material, denser material sank to the middle, you know, differentiation happening. And then the low density anorthosite type material would have been in the outer crust, kind of the way the Earth did as well. But this one cooled off really rapidly because it's so small. Okay. And then, so that was sort of the differentiation stage. The next stage is the cratering and the basin formation. So once the crust had solidified, we could get the cratering to happen. The heavy bombardment period, leaving behind those basins. And some of those basins maybe evolved by upwelling of that magma to smooth it out just a little bit in there. But the older highlands, yeah, that cratering is very intense during the heavy bombardment period. They still have tons of craters on those. Those were like the oldest ones. The upwelling, so kind of the cratering would have kind of created these rings, the multi-ring kind of basins. See how that was sort of shattered, fractured, and dropped down a bit. Multi-ringed basin they talk about, but notice how could smooth that out a little bit. So surface kind of evolution by the upwelling of the magma, but you know, it tended to cool off rather rapidly, so that might have been a shorter period in which it could, you know, renew itself. And so evidence about 4 billion years ago, there was a sudden temporary increase in this cratering, so a secondary kind of late heavy bombardment period that would have put craters on that newly smoothed over Maria. You can get still some craters in that. Okay. And they are interjecting something here that we will come back to when we talk about our Jovian worlds. So Uranus and Neptune, some of our giants out there. This idea that Uranus and Neptune actually formed a little closer in, nearby to our terrestrial planets, and then migrated out to their current positions. And so they're saying here, this hypothesis that the bombardment could have been caused by the final accretion and migration of Uranus and Neptune on their way out to where they are now, that might have created that late bombardment period, throwing out some of the, little protoplanet type of stuff out there, or little planetesimals getting spewed out. Might explain nicely that heavy bombardment period, secondary heavy bombardment period. But once that cratering kind of rate fell rapid, to our current low rate, and so after about 3.8 billion years, now all we see are little micro meteorites, little pits in the rocks. So that rate really slowed down after about 3.8 billion years in there. So cooled rapidly, partially kind of surface evolution in the cracks and crevices, but we are seeing, our vesicular basalt, very similar to the basaltic lava flows that we have here on the Earth. Okay. Those Maria probably formed roughly 4 to 2 billion years ago, and so these are the mare, the darker looking. That's certainly not water, even though they're color coding that here, so kind of a false coloration thing there. But all that cratering in the highlands, and then these are fairly smooth. The Maria are smoother. They got sort of smoothed over with the lava, but you do see some craters here and there on those as well from the late bombardment period. The moon's crust is a little thinner on the side towards the Earth, perhaps due to the tidal effects of their orbit, of the moon's orbit around it. But it's kind of tidally locked, so it keeps the same kind of face toward the Earth. I mean, the moon is rotating, right? But it rotates in such a way that it keeps the same face toward the Earth. So now the moon never had an atmosphere. It was way too small, like we said, the escape velocity, that it could not hang on to any gases, and it never had liquid water on it. So with no air, no water, we saw what that does here on our planet. The erosion was very limited to the surface evolution, except for every now and then we get these little micrometeorites to put little pits in the rocks there. Larger impacts are, rare, not unheard of, though. Okay. So after it lost its internal heat, all the volcanism, so all the basaltic lava died down, right? And we call this geologically dead now. So it doesn't have any kind of internal convection happening. It never formed plate tectonics. The crust never divided into plates. So there are no folded mountain ranges like we see here on the Earth. And it is a one-plate planet. It's not considered a planet, it's a satellite, okay? A moon, okay? But one plate. It didn't break up into several plates like our planet did. That's the moon. A nice variation there, very contrasting to planet Earth. Size had a lot to do with that, right? Whether it could get an atmosphere, whether it could have an ocean or running water, kind of thing. Let's take a look at Mercury, the closest planet into the sun, Mercury. And the names that they get, a lot of these planets have Roman, or I don't know, maybe Greek. I can never keep my Roman and my Greek mythology together. But they used mythology to name a lot of our planets, gods and goddesses and that sort of thing. So Mercury is the messenger of the gods, okay, meaning travels pretty fast, right? So messenger of the gods. So like Earth's moon, so in comparison, Mercury is very small, nearly airless, so it has the hardest time of all the planets in keeping an atmosphere. It's way too small, okay? You also are going to see that it is a cratered world like our moon, and it's dead, geologically speaking. It's dead as well. So small, cooled so quickly that it could not even, develop the plate tectonics, is what it's saying. So Mercury orbiting so close to the Earth that it's really hard to observe from the Earth. So a lot wasn't known about it until along about 1974, 1975, when the Mariner 10 spacecraft, we sent it out and it flew past Mercury 3 times, and so we got some good information about it. Messenger, a newer one even. Messenger flew by in 2008 and 2009 and gave us a nice resolution kind of image of it. And yeah, you can see that surface is very heavily cratered, like the moon is as well. And so yeah, it's going to culminate in even better images. We got another one that happened in 2011 where it did a very close-up study. And it was able to get things about its density. So when you fly a little satellite near your planet, it will be affected by the gravitational pull of that planet. And from that information, they can figure out the density, the average density of the planet. So analysis showed that there were large areas that had been flooded by lava, but then got cratered. So it had, was molten kind of to begin with. Largest impact feature is the Caloris Basin, a multi-ringed kind of fractured basin, 800 miles in diameter. Mercury's very dense. This has pretty much got mostly a metal core and then a little bit of less kind of rocky material around it, crust to it. So the metallic core occupies about 70% of the radius of our planet here. It's essentially a metal planet with a little bit of a thin kind of rocky mantle to it in there. So mostly a metallic planet in there. But yeah, looking at it, we've seen some craters there and some ridges in there. That this is evidence that the entire crust of Mercury shrank and kind of compressed as it cooled. It cooled really rapidly and compressed and kind of shrank up and created some of these ridges, long curving ridges on there. But like Earth's moon, it's very small, right? And that determined much of its history. So the size had a lot to do with it. It was way too small to retain an atmosphere. Lost much of its internal heat rather rapidly. And so we do call it, it's not geologically active. And so, yeah, the differentiation stage to form the metallic core and the rocky kind of mantle in there. Now, we were talking about how when those flybys happen, that magnetic field that we were talking about. So, discovered a magnetic field in there that gave us some further evidence about the metallic core, just how large that metallic core was, because this gave us sort of a density for that, and that indicated that it needed to have a very kind of large core in there. Now up here, it's saying you have learned about the condensation sequence. You have it. Well, when they re-edited the book, they kind of put things in different order. So we haven't learned this yet, but there is something we call the condensation sequence. And so this would be a table in chapter 6, not chapter 12 like it indicates here. But the condensation sequence explains the abundance of metal in Mercury, and we'll talk more about this in chapter 8. But what it has here is this table where you've got temperatures. Okay, this one's 1500 Kelvin, so really high temperatures, meaning objects that are closer to the sun are going to have higher temperatures. And so these are the locations they were forming in our solar system, right? Location from the sun. And what types of material are going to condense out at particular temperatures? Well, being close in to the sun, Mercury would have a higher temperature in that location, and the types of materials that are going to condense out at those higher temperatures are the metals, the metal oxides. Okay, so an object from the temperature of its formation region in there, this would be where Mercury would be. If we go a little bit cooler temperatures, this This is where you'll get the metallic iron and the nickels, okay? Cooler still, the silicates, which are the majority of earth rocks are silicates, okay, silicon and oxygen. Feldspar is another type of very abundant rock here on our planet, something like Venus. Triolite is an iron sulfide, so again, temperature's kind of cooling and this type of material can come out. We see this on Earth, we see this on Mars as well. Things like water ice. Now you have to be far enough away from the sun that we can get some water ice to form, right? So the Jovian planet, like a Jupiter, let's say. And then how about ammonia ice? How about methane ice? How about argon and neon ice? You gotta go way out there like where Pluto is. And so this is a fantastic condensation sequence that helps us figure out the composition of our planets based on how far away they are from the sun, because what temperature were they forming at in their location around the sun. Okay, a very nice one. We'll revisit that again. But kind of drawing on that, they kind of are proposing the composition of Mercury being, you know, mostly this very large core, and they can also base that on the average density, a very high density for Mercury, right? A very large mean density or average kind of density in there. Mostly iron. Okay. All right, let's see. Major impacts, so sort of the surface evolution sort of thing. It got the major impacts, but then wasn't able to resurface that. So second stage, sort of the planet, the cratering and basin formation. A little bit of lava welled up to fill some of the lowlands like it did on the moon, but it lost its internal heat rather rapidly. So it's a large metal core that kind of contracted a little bit and compressed kind of its crust up, eventually breaking it, forming those ridges. And so Mercury does not have an atmosphere, so it can erode, right? We can't get any kind of a water cycle going on with no atmosphere. So it has changed very little since that lava last hardened. Amazing that you can look at that and you can be looking at it the way it looked billions of years ago, because it really hasn't changed much since then. So now it is a one plate planet, like Earth's moon. Geologically dead, we would call it, and it's one plate. It never broke into plate tectonics like our Earth did. Okay, Mercury, Venus, the next one out. So Mercury and then Venus is out a little bit further. And Venus is about the same size, 95% the size of the Earth. You might expect it to be very similar to the Earth. Has a similar average density. So the materials, the layering of it's pretty similar to the Earth. And it's only about 30% closer to the sun. So we're thinking, well, maybe it's similar, but no, it's very, very different. So the surface of Venus is hidden below a very, very thick atmosphere. Only in the last few decades have we been able to discover that Venus is sort of this hot desert world of volcanoes, so volcanism going on, lava flows, impact craters lying at the bottom of a deep, hot atmosphere. This is the runaway greenhouse effect we talked about before. So we won't be able to visit the planet Venus. No spacesuit that we can make could help us survive that. But they have dropped some probes down and taken a look at Venus that gives us some kind of clues to its past. But Venus, the Roman goddess of love, is Venus. So again, the mythology in there. So composition, temperature, density, atmosphere, making it more like Hades than heaven, they're saying here, because it's very, very hot there. Air is unbreathable, it's very dense, very hot. runaway greenhouse effect on here. And so what's going on, you know, they have sent some space probes down there, okay, that survive and descend through the atmosphere. Some of them even made it to the surface of Venus and signaled back some good information from it. But the atmosphere is about 96% carbon dioxide. And we learned what carbon dioxide does here on our planet, the greenhouse effect, kind of keeping our temperatures within a normal, comfortable range. But we have trace carbon dioxide, right? We are adding a little more carbon dioxide to our atmosphere, but it's small amount. You know, we're mostly nitrogen, good amount of oxygen in ours, and some trace of carbon dioxide. This guy here, or this woman here, Venus, has 96% carbon dioxide. That's a lot. Then we got some nitrogen, then we got some argon, sulfur dioxide, that's some bad stuff. Sulfuric acid, can you imagine sulfuric acid? Hydrochloric acid, hydrofluoric acid. These are awful and very strong acids. So this would be inhospitable, to say the least, here on Venus. So tiny bit of water vapor, but deadly unpleasant here, and probably smells bad, you know, the sulfur dioxide in there. So unbreathable atmosphere, extremely dense, 90 times denser than Earth's. So yeah, extremely dense atmosphere in there. Surface temperature hot enough to melt lead. Thick atmosphere creates a severe runaway greenhouse effect in there. And so problems with that, the infrared radiation not being able to escape because of all that carbon dioxide, making it very opaque, right? So it can't escape back out to space. So overwhelming abundance of carbon dioxide makes that greenhouse effect more severe, I mean incredibly severe, than on Earth. Okay. So what they had to do, because of that thick atmosphere, they needed to map this out in a different wavelength. And even though you see blue on there, there are no oceans. Again, this is sort of that false color coding that they talk about. But the orbiting spacecraft has mapped this out, what the surface of the would look like. And so the radars are, you know, in arbitrary colors here. So the lowlands are in blue, color-coded in blue. It's not an ocean, though. There are no oceans on Venus, okay? But overall, it gives sort of oranges kind of tint to it. But the natural color is probably, you know, grayish color in it. But yeah, and you can see volcanism happening, solidified lava flows in there, so a very kind of volatile planet. Lots of volcanism on it as well. Venus, 85% of Venus is covered in that basaltic lava flow, the lowlands in there. They're not seafloors though. The remaining highlands are not the well-defined continents that we see on Earth. Of course, the Earth is dominated by plate tectonics, but something different is happening on Venus. So the highland, Ishtar Terra, named for the goddess of the Babylonian goddess of love, is about the size of Australia. Mountains on there resembling folded mountain ranges. So there was some volcanism that probably helped build up some of the highlands on Venus. But a very long volcanic history there. We still have volcanism occurring on there, and a variety of features that we get from the volcanism. Long, narrow lava channels, kind of meandering, so almost, but it's lava, not a river, kind of meandering like rivers do. But smaller volcanoes, faults, sunken regions where maybe the magma had drained away, and then the land sunk down. Okay, so the volcanic features such as coronae, circular kind of bulges that they have on there, again, all related to volcanism. These little pancake domes they talk about, kind of pushing up the land just a little bit because of the rising convection currents that's going on internally with Venus. Yeah, and then the corona there as well. Circular kind of features of corona. Large, round geological faults in the crust, the corona here. Due to that rising convection in the interior of Venus. Okay. Still very active as well. Okay, so getting the cratering happening just like it did for all the planets. The number of craters, though, on the crust is not quite as ancient as the lunar Maria, but it's not quite as young as the Earth's active surface either, so it's kind of in between. It has had some resurfacing happening on Venus. It's clearly our geologic processes can't be renewing the Venus's surface as rapidly as the Earth's is, but yet it is resurfacing it. So somewhere, not really old surface like the Moon, but not quite as young generation like the Earth's surface. So the slow surface kind of evolution is somewhere in between those in there. Yeah, and so this is kind of the coloring, sort of the grayish color that we would see as they sent a probe down there in 1970 and the 80s too, and it survived for a little while, the heat and the pressure, and gave us some photographs of it. And so you can see sort of the dark basaltic gray, very similar to like the basalt that I was showing you under the camera from Earth's oceans. So definitely lava based in there. So volcanism is very important on Venus. So we're trying to draw together some of these things to tell the story of the history of Venus. So the thick carbon dioxide atmosphere, what was kind of going on with that? And then the geology that it has. So Venus and Earth have outgassed about the same amount of carbon dioxide, but there's a key kind of difference, that Earth's oceans help to dissolve a lot of our carbon dioxide that we had and turned it into our sediments like limestone, the rock limestone. Well, if all the carbon in Earth's sediments and crust were dug up and converted back to carbon dioxide, our atmosphere would probably have just as much carbon dioxide as Venus's does. Remember, about 96% carbon dioxide? So the fact that Earth had an ocean to dissolve that carbon dioxide, our primary atmosphere, if you remember that, put us on a different trajectory than what we see on Venus, right? That main difference between Earth and Venus is that Venus lacked water, oceans, okay? It lacked that. Quite a different history each of those planets took because of that. Right, and so the process, well, they're saying that it may have had a few small oceans when it was young, but that it was closer to the sun, like 30% closer to the sun, so it could have, warmed it up and, dried up those oceans. And so that prevented Venus from, purging its atmosphere of the carbon dioxide. And so now we got the runaway greenhouse effects onwards of like 880 degrees Fahrenheit. I mean, inhospitable there. And so, yeah, they're mentioning the runaway greenhouse effect on there because so much carbon dioxide, it just intensifies that cycle of warming in there. Okay, and that could have affected the geology of Venus. So it could have made the crust a little drier, a little more flexible, so that it was unable to break like the Earth's crust does. The Earth's crust is very brittle. and broke into the plates, and so we had the plate motion. Well, there is no sign of plate tectonics on Venus, so the crust never broke into plates, so there was no plate tectonics in there. However, we still do see the convection of the magma trying to well up in there, and so it is deforming the crust to make those coronae that we talked about, pushing up the large mountains, Maxwell in there. Some folded mountains, Ishtar Terra, very minor crustal motion, but nothing on the order of the plate motion that we see on the Earth. So lack of water made a very different path for the history of Venus in there. So small number of craters, and that entire crust had been replaced within the first half billion years on Venus. So the volcanism kind of took care of a lot of that. But comparing Earth to Venus can reveal more about our own world's volcanism and our plate tectonics. So doing comparative planetology is very important in learning more about our own planet as well. Not just because it's very interesting to learn about these other worlds. So that was Venus, right? So we had Mercury, Venus. We've already talked about the Earth and the Moon. And so now the fourth terrestrial planet is Mars. And so Mars is the Roman god of war. And Mars, the mission to Mars. I mean, we're seriously planning to man or woman setting foot on Mars. That's in the works. But it's an inhospitable world, like the Moon as well. So you need, a spacesuit for that, heated, pressurized, but Mars is not as inhospitable as the Moon, and we've been to the Moon. So yeah, that is in the works for that. And it's more interesting, let's say. It's got some weather, it has a very thin atmosphere, some complex geology, it's got craters and volcanoes going on in it, and very exciting, there are signs, some evidence that there was once running water on Mars. That's amazing. Anytime you have a planet that could have pools of liquid water, there's a potential for life. And so there is an exact mission that is purposely looking for signals of life on Mars, okay? Because of that. The evidence that they've seen at one time, they don't see it currently, but at one time there was water that flowed on Mars. So here we are for the Martian air at 95% carbon dioxide. Again, a lot of carbon dioxide in it, 3% nitrogen, 2% argon, and so doesn't have oxygen like we need. So yeah, we're not going to be able to be there without a spacesuit. And that is similar to the composition of Venus, if you recall. But why is it so different than Venus? And so Mars is smaller, right? Mars is smaller for one thing. It does retain just a small atmosphere. So size has a lot to do with how much atmosphere a planet can retain. So that is less than 1% as dense as Earth's atmosphere, and 1/10,000th less than Venus's atmosphere. And there's very little water in the Martian atmosphere. It really has a hard time hanging on to any water vapor because the Martian atmosphere lacks ozone, an ozone layer like we have here on Earth that protects us, right, from the lethal rays. So without that ozone layer in the Martian atmosphere, the rays, the ultraviolet rays, will come in and dissociate any water vapor that it has in there. It will break it apart to hydrogen and oxygen, right? H2O, water. Hydrogen moves extremely rapidly and Mars can't hang on to it. And then the oxygen. So it can't hang on to the much atmosphere and no ozone layer, and it's just breaking apart the water vapor, and so it can't set up, like precipitation and things like we would get here on our planet. So yeah, it can't rain down water on Mars, not currently anywhere. And so it cannot survive on the Martian surface, and the air pressure is way too low. Any liquid water would just kind of boil away immediately. The polar ice caps, there have a little bit of frozen water, but it's really carbon dioxide rich here, which we end up calling dry ice carbon dioxide in there. But so whatever water is present on Mars is frozen. It's probably within those polar ice caps if we're going to find the water in there. Or maybe permafrost, permanently frozen in the soil kind of thing. But carbon dioxide, frozen carbon dioxide or dry ice at the poles, probably a little bit of frozen water on the poles of Mars anyway, but certainly not a flowing river or an ocean, not nowadays anyway. So Mars is very thin atmosphere in there. But perhaps, climate once permitted liquid water to flow over the surface. Like I mentioned, they do have some evidence that maybe in its past it was able to. But being a terrestrial planet, it should have outgassed significant amounts. So outgassing, releasing of gases from rocks is what outgassing means. So carbon dioxide, nitrogen, and water vapor. But it's a tiny little planet, so it can't hold on to its atmosphere very well at all. And so rapidly moving gases like a hydrogen, let's say, these are going to escape to space very easily. So it can hold on to it very well at all. And the temperature of its planet, it's colder. The gas molecules are traveling a little more slowly. The ozone layer, like I mentioned, our ozone layer protects us from that UV radiation, right? But that sunlight UV photons are going to break down any water molecule, right, to hydrogen and oxygen. And the hydrogen is going to go off into space quite easily. And the oxygen can combine with the rocks and soils and create those. But it may have had a better atmosphere when it was younger, but it's saying here that it has lost much of that direct escape because it's so small, and the UV problem, destruction of it. Okay, so maybe it was able to permit the water at one time, but it certainly does not now. It's a very cold, dry kind of world. Here we've had some orbiting satellites that are showing, again, we got some color coding happening on here, so there's no water. The blue does not mean water at all. But yeah, we're seeing some highlands at some of these. Here's Olympus Mons is just like a volcanic mountain that is very, very high. It kind of dwarfs our mountains here. I think they'll do a comparison of a earthly volcanic mountain and a Martian volcanic mountain in there, but heavily cratered in some locations, being able to smooth out from volcanism in other regions, so a mix in there. But volcanoes on Mars are of the variety that we call shield volcanoes, and shield volcanoes would be similar to what we see in Hawaii, the Hawaiian Islands, the Hawaiian Island chain. Those are all shield volcanoes, and so that would be similar to what we're seeing here on Mars. They're very broad and they have very gentle kind of slopes, and they really cover a great deal, an expanse of real estate, honestly. But here on Earth, the shield volcanoes are produced by hot spots. So you have plumes of magma, these extra hot little spots. And then because here on Earth, we have plate tectonics, that the plate would pass over that hot spot and create the volcanism when you're over the spot. So the big island of Hawaii right now is where the active volcanism is, but there's a whole chain of volcanic islands, the Hawaiian Islands. But once here on Earth, the plates move off of that hot spot, that island is no longer volcanically active. It moved away from the hot spot. And so then just the part of the crust that's currently over the hot spot is the active one. So that's a shield volcano, and that's how that works here on the Earth because we have plate tectonics. Well, on the Martian planet, it doesn't have plate tectonics. And so that land will stay right over that plume of magma, and you can really get some very, very large Olympus Mons there of shield volcanoes, and so it becomes so much more thick than here on our planet because we got plate motion happening. So in comparison, they are taking the Mauna Loa in Hawaii, the largest volcano on Earth, right here. Whoop. Okay, it's the largest one here on our planet. But look at Olympus Mons on Mars in comparison to that here on our planet. So what is happening on Mars is that it does not have plate tectonics. Plate tectonics did not develop, and so therefore the crust is thicker, and you can get your mountain building of the shield volcanoes to really just continue to get taller and taller on Mars, okay, in comparison. And they're just kind of showing how our shield volcanoes here, the Hawaiian Islands. So here's the active volcanoes when the plate is right over the hot spot, right? But these had moved, okay? Kauai at one time was over the hot spot. Now it has moved away, and it's no longer volcanically active. And so that's what they're talking about. We have plate tectonics happening on ours. The lack of that plate motion on Mars just allows that rising magma to continue to repeatedly build up the crust in that same location. So we're getting these gargantuan, mountains in there. So moving plates have not formed on Mars, and those rising currents of magma and repeatedly just heating the crust in the same place and creating those just gigantic mountains in there. So yeah, and we've had some rovers out looking at the surface of the planet. And like I mentioned, this kind of quest for signs of life, and so they're really interested in water. Can we find any water? But we cannot expect to see water on Mars' surface now, okay? Low atmospheric pressure and the temperature, it would just kind of boil away on there. But had it in the past, and there are finding some clues that yes, it has more than likely had it on there. So some orbiting spacecraft, flown around kind of thing, but the rovers on the surface were the most kind of proof positive for turning up signs of past water on there. And so very striking here in 1976 for the Viking spacecraft, but what they were revealing in some photos were these outflow channels. And so these outflow channels do resemble things like rivers that we have had, little streams and channels that we have here on Earth. They resemble that, kind of being cut, something like the mighty Mississippi kind of thing, of water flowing down and carving out the land surface. And so these outflow channels resemble what we have here on our planet that we understand is from carving out of water flowing through. And so that's something. Valley networks also looking like meandering riverbeds. Water does meander and cut kind of in a back and forth sinuous motion, call them meanders. And so they do look like meandering riverbeds with some sandbars, even some deltas, and tributaries. So tributaries feeding into the main flow channel. Yes, so signs that water was at one time flowing on Mars, and this is very, very exciting for this. So some good information there from the studies of searching for water on there. Has been met with some good success on that. Let's see, I think they had, well, here they're talking about the rover's Spirit and Opportunity. In 2004, actually rovers that were on the surface, not just flyby kind of thing, but areas that they kind of went over, areas suspected of having water on their surfaces, and some exciting discoveries coming from Spirit and Opportunity. One here with some close-up pictures of these little kind of concretions, circular looking, they call them blueberries because they just kind of look circular, but they are hematite. Hematite is an iron oxide mineral, okay, here on our planet. So iron and being oxidized kind of thing, you had to have water for a mineral here on our planet for that to have formed. And so their conclusion is that those little concretions of hematite must have formed in water in the past. So there had to have been a history where Mars contained some water. And then the cross layers, the ripple marks. I mean, here on our planet, we do get in the sedimentary rocks ripple marks. I don't know if I have one. Oh, it's too big for me to pick up. But I do have a rock that has ripple marks in it from Earth, sedimentary rocks, where we can kind of get that frozen in time. And so they have found things like that. Some ripple marks in the sediment in there. And so exciting discoveries that at one time Mars did have water on it. In 2008, the space probe, the Phoenix, landed in the North Polar region of Mars, and it did uncover a water ice frozen in the Martian soil. So right now it's permanently frozen, so we don't have any running liquid water on Mars, but some frozen ice water. Very interesting. So here, you know, we're looking that water is essential for life, right? So if Mars had running liquid water at one time in the past, that is why they have this mission to search for any signs of life that may have existed there. And so that's something that they're currently working on, a main mission for that. So the planet began differentiating, so our different stages that we go through, of course, completely molten, and then began to cool and differentiate. So it had its crust, its mantle, and its core, similar to the other planets. And it's revealing that dense core, but not really a planet-wide magnetic field. So a very weak magnetic field in that differential rotation may not have been, you know, strong like on the Earth kind of thing. So that core must cool down rather quickly and kind of shut off the dynamo effect that would have made a nice magnetic field in there. The crust of Mars is very thick in contrast to the Earth, and it does not have plate tectonics, so that does allow for very, very large Olympus Mons there, very, very large mountain volcanic kind of a region in there. The cratering, so the cratering in the basin stage may have broken up or at least weakened some of the crust to trigger some lava flows in there to smooth out kind of some of the basins in there. And so some surface evolution could occur, so you do see a lot of smooth places in there that could have surface evolved any craters that would have been in that region. But the moving crustal plates never dominated on Mars, okay? So there aren't any of the folded mountains, no signs of the plate boundaries on that. And so the small little planet cooled very rapidly. Crust grew very, very thick, so it has a much thicker crust, and it had no plate tectonics, right? So really forming some large crustal places in there. Okay. Volcanism, so we still do see an occasional eruption of the volcanism, but the planet has lost much of its internal heat, and so most of that volcanism would have occurred long ago. They do feel that at some point it did have water, running water on it, enough to, abundantly flow like a river and possibly even fill an ocean. Very exciting to speculate on that. But perhaps probably the age of water was 3 billion years ago, but changed over time. The atmosphere became thinner. Can't really hold on to your water that way. Doesn't have an ozone layer, so atmospheric gases and water just escaped to space, and it can't capture it. So the volcanic activity, it's nearly stopped. So, with volcanism, you can release water vapor with volcanism, but that's kind of died down. So it's not replacing any water that it's losing in its atmosphere now. Any remaining water would be frozen, probably in the polar ice caps, maybe deep in the Martian soil, permanently frozen, so the permafrost that they're talking about. And water is the first necessity of life, right? We got to have water. And so the fact that it did exist on Mars, the speculation that it did exist on Mars, very exciting, and definitely a mission that they are trying to work on with rovers out there. And we're going to Mars. And so maybe one day an astronaut's going to stumble down an ancient stream bed and turn over a rock and oops, maybe find a fossil. That would be incredible. I hope I'm alive to see that. But we don't know right now. Right now, there has been no evidence of life on Mars. Okay. All right. Mars has some moons. Mars has a couple moons, so Mercury doesn't, Venus doesn't. The idea is they are way too close to the sun. The sun would certainly interfere with any kind of trying to keep an orbit around one of those planets. Yeah, they're just too close to the sun to have a satellite or a moon. But Mars is, out there. The Earth has one. Mars has two. And look how oddly shaped they are. They are misshapen in there, and you do see craters on them, so they got cratered as well. But Mars has two, Phobos and Deimos, or Deimos. These are, interestingly, the horses that pull the chariot of Mars, the god of war. And that was the name of the horses. So interesting that they would name those Phobos, fear, and Deimos, what is it? Fear and, I wrote it somewhere. Panic. Deimos, panic. Fear and panic. And they named them, after the Roman mythology. But these, they believe, were captured. Not like with, an impact, large impact like our moon, but these were captured objects. And so they do think that they were captured asteroids. And so some rocky material that gets left over, debris, that gets left over that didn't get swept up into a planet during formation time. And so some leftover debris that kind of just got into the orbit of Mars. And so these are the two smaller. They're not really large, if you can see, 28 by 23 by 20 kilometers in diameter. So they're small, they're irregularly shaped, and so their thought is that these were captured asteroids, which we'll find that, a lot of the larger planets do capture things like that. But this is far enough out that it could capture a couple of those, but they're very small. Okay. All right, so let's see. These moons don't have any kind of evidence of any internally geologic activity on them. you noticed that one was very cratered, so it wasn't able to smooth that out with any kind of volcanism on it. But, you know, some of those might have some water on them. And this idea that maybe we could build a colony on one of those moons, right? And get some water or whatever from that, and then, you know, do our thing on Mars. I mean, you know, you got some plans going on here. But they may have water on them. We don't know. Maybe deep down in the beneath the surface on the rocks, deep interiors. So maybe we could colonize on there and use that water. Who knows? I'm speculating on that, but it is fun to think about those things. So that was Mars. That was the last of our terrestrial planets, the innermost 4 planets, and we included the moon in that as well, just to get the variation and help us with the history of, you know, the differentiation, the cratering and basin period, and then that slow kind of surface evolution is a way that we can kind of piece together and do this comparison. Comparative planetology really kind of gives us something of what the early kind of solar system went through, how it evolved, looking at compositions. So try to remember our compositions, rocky and iron, the condensation sequence that we popped up there. That'll come back to us again when we study our Jovian planets, and when we look at how the solar system originated as well. So try to keep all these little details in mind. And so that concludes chapter 6. Make sure you go through all your bullets on the study guide, and if you have any questions, let me know. Next time we're going to visit the outer 4, and I am saying 4, but they are going to include Pluto, of our outer Jovian worlds, and kind of piece together the entire solar system, and continue with our study of the solar system. So if you have any questions, let me know, and I will see you next time.